Hello, welcome to podcast number 19. These things are just flying by at this point. I'm still in chapter 4, so picking up where we left off with cyclohexane. This time I'm going to look more at the interactions of multiple substituents on the cycloalkane, cyclohexane in this case. So we looked briefly at the fact that axial has interactions 135 with nearby H is not immediately next to it. So it's not actually an eclipse interaction, but it's still steric hindrance. And so we're going to look a little more carefully at that. So I want to start by first considering the impact of a substituent. Now, key thing to keep in mind is it's three-dimensional interference, not two-dimensional, not one-dimensional. So the more bulk something has, the more it takes up space in all three dimensions, the more likely it's going to bump into something else. We also mentioned that equatorial, so this alignment here, is more stable because it doesn't interfere with the neighboring atoms. So that equatorial down H, that axial up H, that axial up H, and that equatorial down H. This H3 is not going to interfere with them, whereas when it's axial, there's an outside chance it can interfere with the axial H's over there. And specifically, CH coming onto that CH3, if I look at it that way, it can interfere with the other H's. So because of that axial interaction, diaxial interference here, or these three coaxial up H's, it causes this H3 to prefer to fold down and be in equatorial position. Now, the way they studied this is they actually looked at the energetics of how it distributes, and they found at equilibrium that you had about a 95 to 1 ratio, or 95 to 5, 19 to 1 ratio of equatorial to axial. And then by plugging into thermodynamics equations, basically delta G equals K equilibrium, or RT gallon of K, negative thereof, they can figure out what the energetics of it is, and from that deduce what the favorability is, what the energy relationship is. Long story short, mathematically, we conclude that this 95 to 5 ratio equals to 7.06. So, okay, so what I'm interested in here is, I know we can calculate it, probably not going to have you do that, but I do want you to interpret what the numbers mean. So when I consider NH2 instead of CH3, again, it's going to favor the forward reaction, just like this one did. But question is, does it favor it more, less, or the same? So with CH3, you can have an H in the way here. If it rotates 120, one of these other H's will get in the way. And if it rotates 120, the other H will get in the way. So there's three H's who have a chance to rotate when it goes around of getting in the way. When the NH2, your chance just went down a little bit. There is an outside chance that it's actually the lone pair, which doesn't take up so much space, that could be in that orientation. Meaning the interference of this H could happen, the interference of this other H can happen, but not all the time. Only maybe 2/3 of the times that interfering. As a result, you end up getting about 89 to 11, about a 9 to 1 ratio in this case. A little bit better. So in this case, you have about 19 to 1. Here you have about 9 to 1. Again, plugging into the thermodynamics equation, you'll come up with the fact that equatorial is more favorable by about 5.77 kilojoules. So here's what I do want you to be able to do. I want you to be able to give me a prediction of how things will work. So OH becomes a little more important because when we talk about OH, we're talking now about sugars. They're going to have a lot of axial orientations. So sugars have OHs on multiple carbons. Again, I worry about this H interfering, but the H can be way out here most of the time. It can rotate in and interfere, but only about 1/3 of the time is it going to be in this region right here to interfere. So it's going to offer less steric hindrance, less interference. You might also consider the carbon is a bigger atom, so it's slightly longer bond, and it's medium O, smaller atom, so it's going to be a little bit shorter. So that can possibly allow it to overlap and interfere a little bit more. But the fact there's only one H, whereas ammonia or the amines have 2, and then the methyl has 3, interference is going to be reduced. So let's see, 19 to 1, 9 to 1. Maybe this one's going to come around 3 or 4 to 1. So energetics 4.35. As expected, it's coming down. And it's about a little over 4 to 1, 4 to 1, 5 to 1, somewhere in that region. Okay, so this is like 4.5 to 1, a little bit better. So equatorial is still more favorable, but not as exaggerated. So the OH can potentially go axial with a higher frequency. Those become kind of important when we start looking at sugars. Last but not least, I'm going to add the cyano group in. So I know that carbon is bigger than nitrogen or oxygen. And I know nitrogen is bigger than, well, same as nitrogen and bigger than oxygen. So I have 2 very large atoms, which means there's a chance they can get in the way. But again, this is a 3-dimensional phenomenon. And this one gives us a really good breakdown of how this actually works. Because of the sp hybridization, the cyano group is linear. So it's kind of like if I have 3 flagpoles, do flagpoles interfere? Or do you need a flag on them to start interfering? So I don't know if that's a great analogy, but hopefully it makes some semblance of sense. 3 flagpoles, things that 6 straight up, actually don't interfere. So even though C and N are bigger than, let's say, O and H, so in theory, they are larger atoms, so they take up more space themselves. They don't ever go into this region because it's sp hybridized. So it ends up, this one is about a 1-to-1 ratio. So it's only favorable by about 0.71 kcals, which means it's 55 to 45, barely over 1-to-1 ratio. So prefers equatorial, but not by as much as ones that take up more space 3-dimensionally. So our conclusion, CH3 takes up more space in NH2, which takes up more space in OH, which takes up more space in CN. This is going to hold true not only for chair conformations, but also for the Gaussian anti we were looking at earlier in this, when we first started looking at Newman projections. So this concept of steric hindrance, you need to focus on the 3-dimensional nature of what's interfering. So you need to consider that 3 H's take up more space than 2 H's, which take up more space than 1 H, which takes more space than nothing sticking out. No H's or no anything sticking out. So what would you expect for ethyl cyclohexane? So if I consider this, I'm going to erase everything I have here, and I'm going to try to turn one of these into an ethyl group. So the easiest one would be the CH3. Actually, you know what? The easiest one, I think, will be the N. I'm going to get lazy and do it this way. I'm going to make that a CH2. I'm going to put a CH3 out here, and a CH3 here. So if I do that, this CH3 is definitely going to interfere with those H's. So if it rotates around, it'll be an H interfering, or the CH3. So it's going to be worse than a CH3. I'm going to venture to take an educated guess. This is probably in the neighborhood of maybe 10-ish. And this is probably in the neighborhood of about 98 to 2, maybe a little bit higher. So this is a guess. I'm just venturing to guess what ethyl is going to do, but this is what I expect you to be able to do. Make a prediction based on the size of a molecule or a fragment of a molecule, just this ethyl moiety. Okay, on we go. We've done a lot of single substituent on a cyclohexane, so ethyl cyclohexane, methyl amino, and so forth. And we're going to consider 2. And in this case, we're going to consider 1,2, meaning on adjacent carbons. So trans 1,2-dimethyl cyclohexane. So let me double check here. I have 1, 2, 3, 4, 5, 6 carbons in a ring. So that's my cyclohexane. Dimethyl means 2 methyl groups, methyl, 1 carbon, so CH3 and CH3. 1, 2 means they are, if this is carbon 1, this is carbon 2, or if this is 1, that's 2, totally arbitrary. And then trans, word we're going to introduce. Trans means across from, opposite sides. So in this trans scenario, if this CH3 is up, meaning in front of the plane, in front of the ring, I should say, this one has to be in back of the plane of the paper with the ring system. So one is said to be up, the other one is said to be down. Cis, on the other hand, is where they're on the same side. So they're both up or they're both down. I can draw it either way. They're essentially the same thing, just flipped over. So I want to look at these in a little more detail. So first we'll consider the trans. So the chair conformations, I don't care what you make, but if you make this one point up, this is point down. If this one's point up, that's point down. If this one's point up, that's point down, and so forth. As long as you have opposites being point up and point down. So I want to emphasize, if the CH3 is up coming out from us, there's got to be an H down going back. And if there's an H going up or in front of the plane coming out towards us, there's got to be a CH3 in back. They have to pair up like that. I draw in pink to emphasize it, but CH3 is up relative to H. The CH3 is back or down relative to CH, or to the CH3 is down relative to the H. So let's go ahead and draw it. I'm going to draw it out, then I'm going to erase my picture. But again, I like the dot approach, so I'm going to arbitrarily make my lines like this. And then I'm going to just pick randomly that, let's say I make this one up for CH3. I'm going to make that one down for CH3. Makes my H here, my H here. Incredibly ugly drawing. Even my ugly drawing works. So even the ugliest of pictures can still explain it. So let me go ahead and erase my picture and let the prettier one kick in. So hopefully this seems a little more clear to you. But again, same thing. The CH3 is up with this H being down. And then if I move one carbon over here, CH3 is down, this one's up. So note that this is my up one, and that's my down one. Specifically to cyclohexane, I should emphasize this is on an axis. This is axial up, this is axial down. So both of them are axial. So note that this is axial up, this is axial down. Okay. One of the things to make note of is when you flip the ring system, when this carbon comes down, this one has to buckle up, this one buckles down, this one comes up, this one buckles down, this one comes up. So we now have this carbon here down. This carbon here is pointing up. This pointing up one is now pointing down. One down one is now pointing up. This one here, which was up, is now down. And this one used to be down, is now coming up. So everything sort of buckles. If you have a model kit that has at least 6 carbons, which thankfully these come with barely 6 carbons, so good luck making methyl groups, then you can go ahead and draw this. But this structure, the new one we draw, or drew, notice how it's still up. So just like this one is up, this CH3 is up, this CH3 here is down, this is down. So let me go ahead and mark my carbon. So I'll make this one yellow carbon. So in yellow carbon, CH3 is up. And on my, let's go with red. Sorry, it's taking me so much time to figure this out, but that CH3 is down, that CH3 is down, that CH3 is down. So note that up stayed up, down stayed down. So down and up don't change when you change from one chair conformation to the other, when you ring flip. What does change is equatorial and axial. So what used to be axial up is now equatorial up. That's bad planning. Sorry about that. And that's equatorial down. Okay, hopefully this makes sense. Now the question is, which is better? To axial or to equatorial? Well, from what we just learned, axial and equatorial differ by about 7.44 kilojoules per mole. We're talking about CH3s. So this thing's probably in the neighborhood of 15 kcals per mole better than this structure. So you're probably looking at a maybe 99.5 to 0.5 ratio, something of that nature. Equatorial more stable than axial, so the right chair conformation is a more favorable one by a pretty good amount. Okay, we're going to keep playing this game. Take an educated guess where things go. So for cis, again, CH3s are both up this time, so up and up. So let me erase, attempt to write right in the way. So make sure I have this well understood. This one's up, this one's up. So when I flip the ring from one structure to another, both CH3 substituents have to remain up. I could have, like I mentioned earlier, you could also draw them with down and down. So we would have gone with down here, and it would have been the same thing, cis is cis. Okay, so again, this carbon is going to come down. This one's going to go up a little. This one's going to go down a little. This goes to point up. It's down a little and up a little. So when we ring flip it, this one, which I'm going to identify in green, is this carbon. It's got to be up. So let me go ahead and write this in. One axial, one equatorial. Perfect. When I go to this other structure, the green carbon, it is still up. So this CH3 is still up. And then when I go one carbon over to the red one, it is also still up. So up stayed up, up stayed up. Pretty good on this, pretty happy. Let me go ahead and write this in with my incredible writing skills. So one axial, one equatorial. So you have an axial equatorial, or you have an axial equatorial. So which one is more stable? Perfectly identical. So it can go in either structure. It means you have a 50-50 ratio, no energetic change when you go from one to the other, meaning these two are constantly oscillating back and forth. So both conformations have an axial and equatorial, so both are degenerate. Degenerate, I think this might be the first time introducing that word. Actually, I mentioned real briefly when we talked about the sp3 hybrids. Degenerate simply means of equal energy. So both are equally stable, equally energetic, equally favorable. Okay, so now we're going to play a fun game called Let's Draw More of These. So we just did the cis 1,2 and the trans 1,2. So I'll revisit those. Here's your cis, both on the same side. So instead of CH3s, we now are doing dichlorocyclohexane, but same basic idea. Notice this is up and up, meaning this must be up, up. This is axial up. This is equatorial up. If it flips, this one's going to come down, so it's still going to be up, but now it's up in equatorial. This one is going, that one did the thing, this one's going to now pop up, rotates that down, rotates, excuse me. This is going to come down, rotates that carbon up. When that comes up, Cl is going to fold in such a way where it now is in an axial orientation, but still up. So again, key thing when you go from one chair to another, if it's up, it stays up. If it's up, it stays up. But axial becomes equatorial, equatorial becomes axial. Equally favorable, just like we just saw. Same story we just did with the trans. We now have an up and a down. So we have an up and a down. In this case, they're both axial. And as we learned with the dimethyl, unfavorable. Chlorine is smaller, so it's going to be unfavorable, not nearly as unfavorable as the dimethyl. Now, for this one, this is still up, but it just became equatorial, where it used to be axial up. This is down and axial. It's still down, but it's now equatorial down. So this is a case where that is your more favorable species, just like it was before. That's the favored conformational isomer. Now, we predicted that in the first one, it's maybe 15 kilojoules per mole difference when it was two methyl groups. With CLs, much closer to maybe in the ballpark of, who knows, 5-6 kilojoules per mole. Not that much difference like the methyls. Okay, 1 and 3. That's where it's going to start getting a little more interesting. So I'm going to say up and up. So up and up. And the best way to draw these, let me go ahead and revisit this. So I'm going to again draw my parallel lines, put a dot here, a dot here. And I'm going to arbitrarily pick this carbon as my first carbon. That's 2, that's 3, that's point up, so it's got to be axial up. So that's how I get it. Just arbitrarily pick anything. Notice I've had a tendency to pick this point over here for carbon 1, and then default this to 2. Make that 1, default that to 2. Make that 1, default that as 2. Okay, just an easier way to just have a habit of how to draw these. So they're axial, axial. And when it flips, it is still up, but now equatorial. This is also up, but equatorial. So just like this, they have the same interactions. Now the difference that we'll run into, when they're 1, 2, they have a gauche interaction. So it's going to make it more pronounced. So actually diaxial offers some favorability over diequatorial. But when they're all the way away like this, there's no axial equatorial interactions to worry about. So this diequatorial is favored over this diaxial by even more than the 1, 2. So I'll go into more detail that down the road, but want to introduce a cool little shortcut. So I'm going to call it my line trick, where if you want to decide whether something's cis or trans on a cyclohexane, Ernie 6-member ring in chair conformation, draw a line between the 2 carbons involved in this. They have substituents involved in the comparison. So those 2 carbons, and if you draw a dashed line like this, from that carbon to carbon, note that the 2 CLs are on the same side of that line. If they're on the same side, they are cis. If they're on opposite sides, they're trans. So for this one, cis because they're both up, both on the same side. So if I drew this line for this other one, they're both on the same side of the line. So cool little trick. So let's see if we can apply this to 1, 3. So 1, 3 trans. I'm going to do point up and point down this time. Not sure why I switched. So if I have one up, then the other one must be down. And I pick the furthest point to the right as my starting point. Okay, I'm going to erase that. That's how I'm going to draw it, but notice those are not the best line of drawing, but they're on opposite sides, so they're trans. Okay, so there's my up, down, my trans. So for this one and this one right here and here, I'm going to draw my line. So they're on opposite sides of the line, so they're trans, and then I'm going to draw a line there. So it makes no difference which structure we draw in. And also want to emphasize, this is axial and up. This is equatorial and down. This one is still down, but now axial. This is still up, but equatorial. You have one equatorial, one axial, means these are degenerate structures, degenerate conformational isomers. Finally, we'll look at the 1, 4. 1, 4, they're both up when it's cis. And again, I could draw both down as well, but I'm going to stick with up. So here's there and there, here and here when I ring flip it. So this was point down over here. It now goes to point up. This was point up here. It goes to point down, and everything else flips accordingly. So this was up equatorial. This is up and axial. This one stayed up, but it flipped to axial. This one stayed up, but it flipped to equatorial. So again, ax-ec and x-ax equal energies, degenerate structures. There's my line. They're on the same side of the line. There's my line, same side of the line. So they are both cis. And then finally, here's my trans, up, down. So in this structure, I have an up and a down. The up is axial. The down is equatorial, also axial, excuse me. And then when I flip over this structure, it stays down, but it's now equatorial, stays up, but it's now axial. And again, drawing my line, they're on opposite sides of the line, so they're trans. Opposite side line, so they're trans. This works really, really well, except the very, very rare case, and honestly, it's probably easier to just see it than it is to anything else. when they happen to be on those substituents there, notice that if I draw my line from carbon to carbon, notice these two are on opposite lines, but these two are on the same side. So that drawing trick breaks down when it's 1, 2 here. But easier way to look at it, instead of the line trick, you just flat out look at it and have an easier time. So if it's up and down, so axial down, axial up, those are opposite sides. One's going up, one's going down. That hopefully is easier way to see it. Okay, so we have our cis and trans, we have our relative energetics. So what I'm interested in, what happens, everything we looked at was with 2 CLs, it was dichloro, 2 methyls, dimethyl, or just monosubstituted. It's going to get a little more complicated when we start looking at other structures. Also, I made a prediction earlier, if methyl was around 7.6, I told you ethyl is probably around 10, clearly way off. It ended up being 8, meaning the structure is going to rotate in such a way where it doesn't equally populate the H, and the CH3 all spending time in the way. It's going to actually rotate in such a way where H's are in the way most of the time and CH3 very rarely. So it really doesn't go up by that much. So instead of 95 to 5, compared to, I think I tried to commit to, it was 99 to 1 or something beyond that. Instead it's just 96 to 4. So here's where it gets really interesting then. I don't know. I think it's interesting at least. This is an H, an H, and an H, all equal, all spending equal time. This is an H, and a CH3. These two spend the bulk of your time. Same thing on this one. You have an H, CH3, and a CH3. H spends the vast majority of the time, so really it doesn't go up by much. But suddenly when you make it 3 CH3s, so you can't put an H in there, it has to be a full CH3, which definitely interferes. Notice how much it goes up by. It goes up drastically. We're going to take advantage of this group right here called the T-butyl group and put that on the chair because it is so unfavorable to put this in the axial position that it forces the structure into a certain shape, certain conformation, and it allows us to do specific stereochemistry, which means chemistry at a carbon from a very specific angle. That'll make more sense, hopefully, down the road. But basically, this is our bulky group that locks structure into a certain position. But we're going to consider 1 and 3, just arbitrary. I could have done 1 and 2, 1 and 4, but I'm going to consider 1 and 3, methyl cyclohexane, 3 methyl, and then 1 chloro. So that means we're drawing the following. Let's say carbon 1, 2, 3. So I can make this chlorine, that methyl. I could actually also make this chlorine, 1, 2, 3, and that methyl. It really doesn't matter. Nomenclature sort of takes care of itself. Carbon 1 is arbitrary. We call it the one with chlorine on it because chlorine wins alphabetically. So on my way on this one. So I'm going to call this carbon 1 with a chlorine, this one carbon 3 with methyl. Just going to count in this direction. Trans means one of them has to be up, one of them has to be down. So that one's up, methyl group's down, as I've drawn. Okay, so if this ring flips, we know this comes up, this goes down. Anything point up is now point down is point up is point down is point up. So this has to be point up on the left side, and this group has to turn into a point up over on the end of the structure. Up stays up, down stays down. That's the one thing that's absolutely essential. But equatorial is going to eventually become axial. Axial has become equatorial. So when this thing flips, this is going to come up. This point up is going to make the chlorine up in this position. This is a point down here, so it's going to become a point up here. So the CH3 still has to be down. Notice it is down because axial will be up. So this first carbon here is this carbon here. And the chlorine is going to go from up in equatorial to up in axial. So up stays up. This carbon here is going to be this carbon here. CH3 is down, so it has to stay down, but it's going to go from axial to equatorial. Okay, I'm going to do a little more drawing associated with this. Just emphasize that it really didn't matter how I drew it. So if I wanted to change the chair a little bit, and instead of having CL up and CH3 down, could also do it with a CL down and the CH3 up. It makes no difference. So that's what I'm going to switch. So my CL is going to be down instead of up to start. CH3 is going to be up instead of down. So this is that same carbon with chlorine. It's going to match over here. So down stays down. Point down has to invert to become, or excuse me, point up has to invert to become point down. This carbon is point up. It's going to become point down. Up has to stay up. So my chlorine on 1 is down, meaning my methyl must be up. Chlorine is down, so my methyl must be up. Equatorial on 1 turns an axial on the other, but down stays down. So second carbon, consider the CH3. CH3 is going to be up. It's going to be up, so it has to stay up, but it's going to go from axial to equatorial. So axial up to equatorial up. Up stays up. It's the energetics we have to consider. So whether you want to compare these two structures to these two structures, it makes no difference as long as they are trans. One is up, one is down, one is up, one is down. Doesn't matter which one you're doing, but we are going to try to make a decision. So I'm going to start with this, the bottom two, just because there's a little more room to write in here. When I have a C3 axial, that is going to cost me 7.6. And when I have a CH3 or Cl, excuse me, equatorial, it's going to give me 2. So that's favorable by 2. This one's favorable by 2. You could say this one's unfavorable by 2. And you can say this axial for CH3 is unfavorable by 7.6. And it's favorable in the product by 7.6. So overall then, this unfavorable by 7.6 compared to this one, only favorable by 2 means this is 5.6 unfavorable. This is 5.6 favorable. So it's definitely going to push forward in that direction. It's favorable. You're going to gain 5.6 kilojoules per mole when you go in that direction. So your preferred conformational isomer are the CH3 equatorial and the Cl axial. Doesn't mean this other one can't exist some of the time, but based on those numbers, the difference of 5.6, I'm going to estimate here, but considering these numbers amount to this, I'm going to say we are roughly in the ballpark of around, I don't know, 90 to 10, 89 to 11, something like that. You'll also notice real subtlety, but the number that appears in the book, 4.2 and 83 to 17, is close, but doesn't quite match what I put earlier. And that's because every single textbook, I'm basing mine on numbers that I had in my book. This is based on the textbook we use in the class. They are ever so slightly different. And that's because no two books ever match. We generate things whatever way we generate. So my point to you, the reason I'm bringing this up, don't memorize these exact numbers. Don't memorize any numbers I give exactly. Know them generally. And if you ever run a test, my test or any test you take in the future that gives you numbers and they differ from what you learned in my class or any other class, go with the numbers as they give them to you. These are all subject to different interpretations of the experiment, and they're also variable with temperature. So notice no temperature is listed here. I didn't list the temperature in mine. So we'll just go with these being rough numbers. I know I'm over beating this into the ground, but no numbers in general, see trends, but don't memorize exact numbers. Okay, so this finishes this topic off. We're going to move on to something called constitutional isomers, and those will deal with different positions on the actual structure. So we did them in a subtle way. We did 1,2 compared to 1,3 compared to 1,4, where the two substituents were on different carbons. That'll be our next topic. So have an absolutely wonderful time studying for the tail end of this chapter, and I will see you at the next podcast. Bye.